Hello, I'm Wallace Lages with Northeastern University. My co-author is Nani Strang with Virginia Tech. Some of you may know of Processing, which is a desktop IDE and framework created by Casey Reyes and Ben Fry for generative art and prototyping. It allows one to easily create audiovisuals called sketches using Java programming language. There are a few applications for producing art in VR, like Tiltbrush and Google Blocks, but none of them allow prototyping of interactive or the development of creative experiences. There are a few applications that can generate VR environments. I will quickly mention a few of them. The University of Massachusetts Lowell created MyVR, which is a browser-based programming educational platform. It allows users to generate 3D environments in the desktop using JavaScript and then visualize the scenes using WebXR. Another well-known educational platform is Alice. It's a block-based programming environment like Scratch. It eliminates syntax errors, making it more accessible to novice users. Similar to MyVR, users can develop in the desktop and visualize it in VR. A different approach is the one used by 3D VPL. It's a programming environment from Florida International University. 3D VPL display code structure in the 3D environment, allowing students to use VR headsets to visualize code and relate the spatial representation with the textual code. What is common in all these applications is the use of programming as a way to express algorithms that operate in 3D space. For example, changes of coordinate systems, vector operations, and other types of transformations. Also, because those are spatial operations, this type of programming is the one more likely to reap benefits from VR environments. So we built Abacus, which is a VR programming environment for rapid prototyping and procedural generation. Abacus supports two modes, the VR and the desktop mode with the same functionality. Abacus is the block-based language similar to Scratch. The blocks can be accessed in panels inside VR. It has different blocks to support all major programming operations, plus loading different types of assets. There are special blocks to react to events, and even retrieve information from tracked controllers. Abacus also provides support functionality, for example, for loading and saving programs, teleport for locomotion inside the virtual space, and support for video tutorials. This is an example of an environment created by procedural programming. So the main question is an environment like Abacus effective to get students more comfortable and excited with 3D programming? Most prior studies of VR effectiveness for learning have focused on visual domains, such as like medicine and engineering. And although there are multiple results about the impact of 3D non-immersive programming tools, there is limited understanding how these results would transfer to VR. So we set to answer two questions. First one is related to the impact of VR on students' perceptions of competency in programming. And the second one is related to how VR itself impacts the performance of 3D programming tasks. Our first question is related to the concept of self-efficacy. Bandura defines it as the beliefs about one's ability to perform the actions required for achieving a specific objective. Self-efficacy has been shown in previous studies to be more important than other factors such as intellectual ability or previous mathematics knowledge on CS education. We operationalize the 3D programming self-efficacy by extending an existing scale for general programming by adding questions around fundamental tasks in 3D programming. The final scale has shown a good reliability with a Cronbach alpha of 0.82. We also consider spatial ability since it has been associated with increased performance in visualization tasks in multiple domains such as mathematics, engineering, and architecture. We used the cube rotation test to operationalize that. We used the between subjects design with 20 participants assigned to the desktop computer environment and 20 to the VR programming environment to evaluate the system. And each group did two tasks, which we call the procedural task and a math task. The procedure was as follows. Participants completed the background survey before arriving. Once they arrived, they were assigned to the VR programming or to the PC programming environment. Those in the VR would answer the VR experience questionnaire. The self-efficacy questionnaire was taken as 3 times, before the first task, after the first task, and after the second task. And at the end, participants filled out the system usability scale, and as a TLX questionnaire, and the user experience questionnaire short version. And they study completed with an interview. So for the first task, participants were asked to build a forest in 2 steps. The first step was just to build a line, and the second extended to a field. And in the second task, they were asked to build a solar system, also in 2 steps. In the first one, to make just the sun rotating around itself, and in the second one, add Earth orbiting around the sun. The pre-intervention questionnaires indicated that our sample had different levels of experience and spatial ability, and all participants knew the basics of programming, but all of them were new to 3D programming itself. Most students were from computer science and engineering majors. This plot shows self-efficacy at the 3 points that were measured in the study. After the intervention, self-efficacy increased on average in both VR and PC, but with the largest increase happening after the first test. To test our hypothesis that spatial ability and prior experience would influence the effectiveness of the VR environment, we modeled the percentage of increase in self-efficacy between the first and last measurement using spatial ability and prior programming as a covariate. We found evidence for both main effect of experience, environment, and the interaction of mental rotation and environment. Our model indicates that when controlling for spatial ability, the relative gains are higher for VR users, and that this difference decreases as experiences increases, meaning that our intervention was more beneficial to those with less experience. When controlling for experience, individuals with lower spatial skills showed higher relative improvement self-efficacy in the VR mode than those in the PC environment. And as spatial skills increased, the relative gain of both environments converged, meaning that the VR environment was more useful for those with lower spatial abilities. The behavior of VR participants is congruent with what we call compensatory hypothesis, meaning that participants with high spatial skill gain less from VR because they don't see the need of VR to support their performance. Regarding our second question, we found no significant difference in any of the performance and usability metrics. And our conclusion is that the findings indicate that VR was more effective than PC in raising participant self-efficacy, particularly for students with lower spatial skills and students with low 3D programming experience. Thank you.